All right. Hello, Honors Physics. Welcome to your next lecture video. All of these slides you can also just look at as a PDF, but if you want to hear me talk about them, here I am. Last week we were looking just at the creation of magnetic fields and talking a little bit about the shape of magnetic fields, and we introduced something called the right-hand rule to help you figure out the direction of the magnetic field vectors when that field is being produced by an electrical current. And I have that rule restated here in the top half of the screen, including, I think this is the same diagram that I showed you last week. This came from the book originally. I added one blue vector on it because the arrowheads are a little too small. So to recap, the idea with that right-hand rule is that as long as you're using your right hand, this time I have my camera not mirrored, so it should look correct for you. As long as you're using your right hand, if you let your thumb point in the direction of the current, whatever that is, then the direction that your curled fingers go when you make a fist, that is going to tell you the directions of the magnetic field vectors. So, as in the example that's shown there, if my thumb goes up because the current goes up, when I curl my fingers, they are going to be going this direction, and that's the same direction as that blue arrow is indicated there to show you which way the magnetic field goes. Now the next couple of sections of the book start talking about forces that magnetic fields can exert on matter. And to determine the direction of the force, you have to think about a right-hand rule again. Technically, this second right-hand rule is the fundamental right-hand rule, or the only real one. All other right-hand rules are descended from this one that I've labeled as number 2. But at this level in intro physics, they're usually presented separately. So technically there's a way to do the same process as number 1 using this other rule, but it's a little bit trickier. So you can just stick with rule 1 the way it's expressed if you want to. But anyway, so the magnetic force exerted on a particle or on a wire that's carrying current is determined from this right-hand rule. This applies for anything that in math would be called a cross product. There's more than one way of multiplying vectors with each other. We talked earlier in the year a little bit about dot products. That's one way to multiply vectors. Cross product is another way to do it. And this is the rule that applies to all cross products. And there's a lot of cross products in physics. So the idea is that, again, with your right hand, you start with your entire hand pointing in the direction of the first vector, whatever direction that is. And then you need to bend your fingers so that they are pointing in the direction of the second vector. And the order does matter here. So if you take a cross product of A times B, it's not the same result as a cross product of B times A. It's not commutative. If you reverse the order of the two vectors, you get a minus sign on the answer. So you do have to know which one comes first to get the correct result. So again, you begin with your whole hand pointing in the direction of the first vector, whatever direction that is. And then you want your fingers to bend so that they're pointing in the direction of the second vector. And that may mean that you have to twist your wrist around, sometimes in very awkward ways. As a physics teacher, this is one of my favorite units to teach because throughout the entire chapter, students are holding their arms up in these weird ways, including in the tests. and so I'm not going to get to see you guys doing that. It's a little disappointing. But after you figure out which way to twist your wrist so that your fingers can go where they need to go, then you just extend your thumb, and your thumb points in the direction of the answer. So I'm going to try to mimic the diagram that's in the lower right, and that's going to be tricky to have it both inside the bubble and getting my hand where it needs to be when it's not mirrored. So I think something like that. No, wait, you need to be seeing my palm. All right, I'm going to turn around. Okay, here's my right hand, and it's in a position similar to the extended fingers that point in the direction of the first vector. I would then need to bend my fingers like this, so they're coming a little bit out of the screen towards you. And if I just extend my thumb like this, that's the direction of the result, or the answer. So first vector, second vector, answer. And notice that once I've got my fingers in the direction of this first vector, for a given choice with my palm, like if my palm is going to point out of the screen like this, I can bend my fingers just a little bit, or a lot, so that they're perpendicular to the starting direction. I can even bend them further than that, so that they're like a full 180 degrees back. But if I start like this, with my palm pointing out of the screen, all of the directions that I can get with my bent fingers also have some component out of the screen. Whereas if I start like this with my palm facing up, when I bend my fingers, they're always going to be pointing at least a little bit up. If my palm faces down, I can get any vector that points down, and so on. So when you're trying to figure out which way to turn your wrist, that can be helpful. Start with your palm facing as close as you can to the direction of the other vector. In most of the examples that you see, all of the vectors are going to be perpendicular to each other, but that doesn't have to be the case. The only angles that have to be 90 are the angles with the resulting vector. So going by the labels, like in that bottom diagram, vector 1 and 2, they don't have to be perpendicular to each other, but vector 1 will be perpendicular to the result, and vector 2 will also be perpendicular to the result. Another way to think about that is that the two vectors you start with, they define a plane in space. Two vectors are sort of like 3 points. They have their common origin point, and then there's like the ends of both of those two vectors. So with those 3 points, you've defined a plane in space with some orientation. Doesn't matter what that orientation is. The resulting vector has to be perpendicular to that plane, which means it will also be perpendicular to both of the starting vectors. So that's the conceptual side about the direction. These are the actual formulas that you would see in the book and that you're going to be using a little bit in the work. So the top equation here is about the force that a magnetic field exerts on a wire when that wire carries current through a magnetic field. And if you have already looked at the YouTube links that I included, you've seen some examples of that with some lab demos. So the way the book writes the equation is this second line, F equals ILB sine theta. A more generic way of writing it is what I have above, with the vector signs on them, and then this times sign is for the cross product. The angle theta that you see here is the angle between the direction of the current and the direction of the magnetic field. So if you want to apply this, again, using this right-hand rule, you want to find the direction. The first vector is you can think of it either as the current or this length of the wire. Current technically is not a vector for kind of esoteric reasons, but you'll be fine for this purpose if you just think of the current as being a vector. So the direction of the current is what you would do with your entire hand. That's the first vector. And then the second vector is the magnetic field, so whichever way the field points, you need to twist your wrist around to find that. And then again, your thumb will be the answer. The equation for the force on a single charged particle that's moving through a magnetic field is very similar. If you think about the fact that a current is just a bunch of moving charged particles, then it probably doesn't seem too surprising to you that the equations are very similar. The upper equation kind of just comes from adding together a bunch of copies of the lower equation. So in both cases, the motion of the particles is your first vector, whether it's a current or the velocity. Either way, you're talking about the motion of the particles. The second vector is magnetic field, and then the answer for your thumb is the force. So if you need to do any calculations, you'll be using this formula. When you only are interested in the direction, then you use the right-hand rule for that. And the other thing I want to point out is that notice these equations both have this sine theta. And again, theta is the angle between the first and second vectors. And the diagram drawn here, that's 90 degrees, basically. Sine of 90 degrees is 1. So if those two vectors are perpendicular, that is when you get the maximum possible strength for the force. 1 is the maximum value for sine. So if the sine is equal to 1, you get the biggest force that you can get. If the angle between those vectors is less than 90 or more than 90, like as they get closer and closer to lying on the same line, the force gets weaker and weaker. And if you think about it, if you were to put in a 0-degree angle or 180 degrees, in either of those cases, the sine function gives you 0, which means that if a particle is moving along the same line as the magnetic field, force is 0. So it's easy for charged particles to move in the same direction as a field. But if they try to move across the magnetic field, they try to cross field lines, that's when you get a force exerted on them. And because that force has to be perpendicular to the velocity of the particle, that comes from the right-hand rule. Because the force is perpendicular to the velocity, that means that if the field is uniform in strength, at least, when a particle goes into a magnetic field, it's going to end up moving in circles. If you think back to when we were studying circular motion, centripetal force, that sort of thing, the way that you get motion in a circle, the way you get uniform circular motion, is if the force on your object is always perpendicular to the velocity. And that is exactly what happens when a particle is moving in a uniform magnetic field. The particle will move in perfect circles. That's kind of an interesting phenomenon. Okay, let's look at a couple examples. A particle with a charge of 2 nanocoulombs, little n is nano, means 10 to the negative 9th. 2 nanocoulombs moves to the right at 20 meters per second through a uniform 0.3 Tesla magnetic field, which points up. What are the direction and magnitude of the force felt by the particle? All right, let's think about the direction first. I don't have to do any math for that. So, particle is moving to the right. The magnetic field points up. So if I look back at the formulas, We're talking about a single particle. The velocity comes first in the equation. The magnetic field comes second. So I need my right hand. Here it is. I need my right hand to initially be pointing to the right. So something like that. All of my fingers are pointing right to represent the velocity of the particle. Magnetic field points up. So with the way I have my hand right now, if I bent my fingers, they're going to point down. So I need to twist my wrist around. I am about to dislocate my shoulder, holding it like this, but I can now bend my fingers to point kind of up. And if I do that, oh, this is not easy. How about that way? Here's all my fingers pointing right. Now my fingers are pointing up to be the magnetic field, and my extended thumb points towards the camera, out of the screen. So that's B. That's B. The force comes out of the screen. Okay. So the direction is going to be outward. If I were going to draw that on a diagram, and I have the answers on the next slide, but if I were going to draw that on a diagram, it would look like a dot or a circle with a dot in it, represent the point of the arrow coming out of the screen towards me. To get the magnitude of the force, I would plug numbers into that equation. So formula read F equals QVB sine theta. Q is the charge, so that's 2 nanocoulombs. V is the velocity, so that's 20 meters per second. B, magnetic field, 0.3 teslas. And then I'm supposed to fill in sine theta. The problem doesn't actually say explicitly what theta is, but I know that the directions are right and up. Right and up are perpendicular to each other, so the angle is 90. So here's all of those results. I've got a diagram drawn for the direction part. Again, the velocity points to the right. The magnetic field points up. And the force points out of the screen. I am now thinking that I did my example wrong. That way is to your right. What is going on? No, that's left. This whole mirroring thing is so weird. Right. Yeah, that's pointing to the right. To me, it looks like left because I'm on the other side. Okay, I did it right. Eesh. Anyway. So this diagram represents that right-hand rule stuff. Again, for the magnitude, just fill the things in. Q is plus 2 nano, B is 20, B is 0.3. The angle theta, again, although it wasn't explicitly stated, is 90 degrees. And if you plug that in, you'll get 1.2 nanometers. A lot of the charges are going to be given to you in units that have metric prefixes on them because a coulomb is a lot of charge. And so if the problem is even remotely realistic, you're not going to see like an entire coulomb of charge. As long as there's only one number that has a prefix on it, you don't have to convert it. Notice that the teslas was just regular teslas, meters per second, just regular meters per second. So the nano on this coulomb here just sort of carries through to the end. If you're unsure about that, if you're uncomfortable, go ahead and convert it. Again, nano means 10 to the negative 9th. So this would be 2 times 10 to the negative 9th times 20 times 0.3 times sine 90. when you plug that in, you'll get 1.2 times 10 to the negative 9th. So it's still nano. So I just carried the nano straight through. Okay, example 2. This one reads very similarly. Particle that charge plus 2 nanocoulombs moves to the right 20 meters per second through a uniform 0.3 Tesla magnetic field. That all sounds really familiar. But this time the field makes a 30-degree angle with the vertical. So the field is pointing mostly up, but a little bit to the right. What are the direction and magnitude of the force felt by the particle? Okay, so let's try to figure out the direction first. So here again, my hand pointing to the right, according to the bubble on my camera. But the magnetic field points mostly up, a little bit to the right. So I'm going to have to flip my hand over in this weird way again. Get over here. So fingers pointing right. Last time I made my fingers point straight up, and then I got my thumb coming out of the screen. But this time I don't want my fingers to point straight up. I want them to point mostly up, but a little to the right. So that would look maybe something like this. Mostly up, a little right. But notice when I extend my thumb, it still comes out of the screen. In fact, I could choose any direction for the magnetic field from, oh, it's so hard to get my hand level. So I could choose any direction for the field in this range, and they would all give me the same answer for the direction of the force, because I don't have to turn my wrist. All of these magnetic field directions have the same thumb position, so they all have the same force direction. So the direction is the same as before. Still is out of the screen. But the magnitude of the force will be different this time because the angle has changed. Remember, because of that sine theta, we get the most force when the two input vectors, the velocity and the field, when they're perpendicular. But now they're not perpendicular anymore. So the answer to this part, the answer to this example, should be smaller than the answer that I got in the first example. So here's a diagram version for the directions. Again, the velocity vector points right, but this time the magnetic field is on an angle. But they still define the same plane as if the field was vertical. So that means that the force vector doesn't change. It still comes out of the screen. And then when I plug in numbers, the only difference in the calculation from last time is the angle. Instead of 90 degrees, it's now 60. You may be thinking, Mr. Stonebreaker, the problem said 30 degrees. What is going on? Keep in mind that this is supposed to be the angle between the velocity vector and the field vector. The 30 degrees that was stated in the problem, that's the angle between the field and a vertical line. So this, I don't have a convenient way to draw on here. This here, if I move my mouse pointer up and down, that's the vertical. So there's a 30-degree angle here, but that's not the angle that you would want to plug into the formula. You need to plug in this angle between the v vectors and the velocity, and that's going to get a complement of 30, which is 60. That's where this 60 came from. So that's an area that you can get tripped up when you're doing calculations with this. Drawing a diagram, always recommended to try to figure out angles, but it's important that the angle you use be the angle between those two input vectors, so the velocity and the field, or the current and the field, depending. Now there's one other trick which I did not mention earlier. I'm going to page back a few. If you are dealing with the motion of a charged particle, keep in mind that this formula has a Q in it. Q is the charge of the particle. So if the particle is positively charged, like in the examples that you've seen so far, the direction that you get from the right-hand rule is fine. But if Q has a negative value, then that needs to reverse the direction of the force. If you take the opposite of a vector, that means turning it around to face the other way. So when you do this right-hand rule process, the result that you get, the direction of your thumb, that's the direction of the force that would be felt by a positively charged particle. If the particle you're dealing with is negative, for example, if it's an electron, and electrons come up a lot, if it is negatively charged, then the force is going to be the opposite of what you get from your thumb. Some students like to use their right hand for positive particles and their left hand for negative particles. If you can do that consistently, then that's fine. That will work. You can use your left hand instead for negative particles. Personally, I use my right hand all the time, and I just explicitly think about the charge at the end. So like after I get my thumb direction, I think, okay, was this positive or was it negative? And then I either stick with the direction I got or I flip it around. And I do that because I don't want to get in the habit of using both of my hands for this, because I'm afraid that I'll mix them up. I'll use the wrong hand. So I just always use my hand, and I think about the charge later. But if you think you can safely choose which hand to use based on the given information, that's fine. Use left for negative and right for positive. That'll be okay. In the questions that I want you to do for your work for this week, there's a mixture of both positive and negative particles. So you'll have to be on the lookout for that. And in some of the videos that I am attaching to the assignment this week, there are plenty more examples, including negative particles. One of them even has a guy doing a demo with a cathode ray. So you can like literally see this beam of electrons because they make the gas inside the tube fluoresce. And he brings a magnet nearby and the beam bends around, and he talks about the direction of that force for those negatively charged electrons. All right, I think that's all I've got. If you have questions, you can come to office hours. I've changed the times this week from last week, but the updated times are listed for you. You can look them up. And that's it. So, hope everyone is well, and I hope that this made some sense to you.